The research introduces a novel approach to inverse design in chemical compound space, combining quantum mechanics methods with machine learning techniques. It focuses on using a variational autoencoder and a property encoder to create a common latent space representation for molecular structures and properties. This approach enables property-to-structure mapping for small drug-like molecules within the QM7X dataset. Applications include conditional generation of de novo molecular structures with targeted properties, transition path interpolation for chemical reactions, and insights into property-structure relationships. The proof-of-concept implementation demonstrates the potential to parametrize the chemical compound space using properties as coordinates, which could accelerate the discovery and optimization of chemical compounds. The findings provide a foundation for future research in inverse property-to-structure design in diverse chemical spaces. This study presents a novel approach to understanding and manipulating the intricate relationship between the properties and structures of organic molecules. By leveraging the comprehensive quantum mechanics data contained in the QM7X dataset, a proof-of-concept implementation combines a variational autoencoder (VAE) architecture with a property encoder to encode molecular structures and their associated quantum mechanics properties. This joint training yields a low-dimensional internal representation common for both molecular structures and quantum mechanics properties, enabling the approximation of the chemical compound space (CCS) parameterization using quantum mechanics properties as intrinsic coordinates for navigating the QM7X chemical space. The modified VAE framework includes an additional network parameterizing the probability distribution psi, z, y, where y represents the quantum mechanics properties. The loss function is modified to include a likelihood term, expressed as a combination of the Kullback-Leibler divergence, the negative log likelihood of the decoder, and the likelihood term. The training procedure follows the standard VAE approach, with the variable z sampled from Q phi, z, x, maximizing the likelihood term. The proposed method accurately predicts the heavy atom composition of molecules and reconstructs their geometries with reasonable accuracy. It also identifies the most relevant properties in the molecular reconstruction process and substructures in the molecular property space covered by QM7X. Furthermore, the conventional multi-objective generative modeling paradigm is retrieved by conditionally sampling in the input space of properties to accomplish two distinct design tasks with well-defined objectives. The study demonstrates the capabilities of learning a CCS parameterization by implementing a geodesic search algorithm, which uses the latent space representation as internal coordinates. This enables the definition of transition structures and the estimation of rotational energy profiles by learning only from equilibrium geometries. Although the current proof-of-concept implementation is assessed only for small molecules, the findings suggest that a CCS parameterization based on quantum mechanics properties is feasible and holds promise for a wide range of applications, including interpretability, generation of de novo molecules, transition path interpolation, and reaction barrier estimation. The methodology employed in the inverse property structure design involves training a variational autoencoder (VAE) architecture to encode molecular structures and their associated quantum mechanical properties. This training utilizes a modified evidence lower bound (ELBO) loss function, ensuring a common latent representation for both properties and structures. The joint training enables the inference process, where the property encoder is combined with the decoder component of the VAE to approximate the CCS parameterization using quantum mechanical properties as intrinsic coordinates. The differentiability of the CCS parameterization allows for identifying the most relevant properties in the molecular reconstruction process and performing various molecular design tasks. The molecular representation and structure retrieval require an encoding that is invariant to translations, rotations, and permutations, strongly correlated with quantum mechanical properties, and invertible. The authors discuss the representation of 3D molecular structures using the Coulomb matrix, which is an elegant and physically inspired descriptor. The Coulomb matrix is invariant to translations and rotations, allowing for the retrieval of atomic positions and species of a molecule up to a chirality transformation. It is defined as a matrix where the indices I and j run over the atoms in the molecule, and z indicates the atomic species. Hydrogen atoms are treated implicitly due to their smaller terms in the CM representation. To retrieve Cartesian coordinates and chemical composition, a two-step process is followed. First, the composition is obtained from the diagonal elements by applying the inverse function and rounding the outcomes to the closest integer values. Then, the set of atomic numbers obtained is used to get the distances between atoms and apply classical multidimensional scaling to the resulting Euclidean distance matrix to get the Cartesian coordinates of atoms up to a chirality transformation. The authors also discuss the choice of representation, noting that a graph-based representation would be beneficial for generative purposes, but for this work, they use the CM due to its efficiency and scalability for inverse design purposes. The research paper presents a detailed table outlining various quantum mechanical (QM) properties considered in the QM7X dataset. These properties include atomization energy, MBD energy, exchange energy, nuclear energy, electron energy, kinetic energy, HOMOLUMO gap, and other dipole moments and polarizabilities. The properties are categorized into structural, global, molecular, ground state, response, extensive, and intensive types. A model trained on these properties demonstrates an ability to reconstruct molecular structures with high accuracy, with the error in reconstructing the Coulomb matrix converging to approximately 5% as more properties are used during training. The model performs exceptionally well in chemical composition reconstruction, correctly predicting the composition for 99.96% of the molecules in the test set. The authors analyzed the model's performance using a gradient attribution map, revealing that certain properties, such as atomization energy and MBD energy, have a significant impact on the model's predictions. This section highlights the model's capabilities in leveraging QM properties for accurate molecular structure prediction and its potential for understanding the relationship between these properties and molecular structure. The performance of the trained model in molecular reconstruction is evaluated in Figure 2. As the number of molecular properties considered during training increases, the average relative error on the reconstruction of Coulomb matrix (CM) representation of structures from quantum mechanics (QM) properties decreases, with a standard deviation per case represented by the orange shadow. A frequency plot of the root mean squared error (RMSD) between the geometries retrieved from the reconstructed CMs and corresponding original representations shows that an RMSD less than 0.7 is an adequate threshold to separate molecules with an acceptable reconstruction of the heavy atom structure in terms of topology and orientation. An analysis of the hierarchy of QM properties reveals that extensive properties are more informative than intensive ones for molecular reconstruction. This is attributed to the fact that these extensive properties depend on crucial molecular features, such as the number of atoms, number of electrons, and geometry, which are also considered in a 3D representation like CM. Consequently, the components of the total energy and molecular polarizability have higher values compared to molecular orbital energies and dipole moment. Interestingly, this finding aligns with the identification of molecular clusters in the two-dimensional principal component analysis (PCA) of the latent space of the VAE encoder, where higher values correspond to better correlation with respect to PCA. The revealed hierarchy of QM properties organizes the QM7X CCS into linear shape clusters containing molecules with the same heavy atom composition, as seen in the two-dimensional projection of the QM7X molecular property space defined by kinetic energy (ECN) and exchange correlation energy (EXX). ECN is primarily influenced by the heavy atom composition within a molecule, while EXX is highly sensitive to the number of H atoms, indicating a dependence on the particular bond types present. A closer examination of one of the highly populated clusters reveals a finer local structure with almost perfect inverse correlation and very compact clusters formed by isomers. This behavior can be understood by considering the qualitative aspects of ECN and EXX, where the dominant contribution to ECN stems from the inner atomic potential, and the correlation between these two properties can be attributed to the balance between the kinetic energy and the exchange correlation energy in the total energy of a molecule. The analysis of molecular properties and their contribution to the output structure is a crucial aspect of this research. Gradient attribution maps are employed to evaluate the relevance of extensive and intensive properties, providing insights into the role each property plays in shaping the final structure. A two-dimensional principal component analysis (PCA) of the latent space is conducted, revealing correlations between property values and PCA components. This indicates that certain properties significantly influence specific components, which in turn affect the overall structure. Quantum mechanics (QM) properties prove effective in identifying molecular isomer subspaces and predicting heavy atom composition. This underscores the importance of QM properties in understanding the molecular structure and composition. The concept of property-based parameterization of the chemical space is introduced, with a visualization demonstrating the overlap between latent representations of molecular structures and properties. This overlap suggests a strong relationship between the molecular structure and its corresponding properties, supporting the idea of property-based parameterization. To establish a self-consistent method for error estimation, the correlation between differences in latent space representation and the quality of reconstructed molecules is analyzed. The results show a nonlinear but monotonic relationship between the error in latent space representation and the RMSD, root mean square deviation, between original and reconstructed structures. This relationship forms the basis for a filtering approach aimed at enhancing the quality of generated structures. In conclusion, this study highlights the significance of molecular properties in determining the output structure and demonstrates the potential of property-based parameterization of the chemical space. The proposed filtering approach could significantly improve the accuracy of generated molecular structures, paving the way for advancements in drug discovery and materials science. Organizing the QM7X molecular property space through two-dimensional projections reveals a hierarchical structure of quantum mechanical properties. Certain properties emerge as suitable local coordinates for exploring specific molecular isomer subspaces. This is demonstrated by analyzing molecular structures within a particular subspace, highlighting the importance of specific properties in distinguishing molecular structures. For instance, certain properties are more effective at distinguishing molecular isomers within a subspace, indicating their potential as local coordinates. This hierarchy of properties has significant implications for exploring the vast molecular property space. By identifying key properties that define specific subspaces, researchers can more efficiently navigate the complex landscape of molecular properties. The learned CCS parameterization enables novel applications, including multi-objective targeted molecular generation. This involves conditional sampling of non-targeted properties while fixing targeted properties, using a multivariate Gaussian regression model to determine the posterior distribution of non-targeted properties given fixed targeted values. This approach allows for the generation of molecules with specific, desired properties while controlling for other properties, opening up new avenues for molecular design and optimization. By leveraging the hierarchical structure of quantum mechanical properties, researchers can develop more targeted and efficient methods for molecular generation and optimization, with potential applications in fields such as materials science and drug discovery. The similarity analysis between the latent space representation from the Variational Auto-Encoder (VAE) and property encoders is presented in Figure 5. This analysis reveals an overlap between the two-dimensional principal component analysis (PCA) of both latent space representations, as shown in Figure 5a. The correlation plot of the root mean square deviation (RMSD) between the original and reconstructed structures versus the latent space difference, increment z, is presented in Figure 5b. The average value and standard deviation of the RMSD corresponding to different values of latent space difference, increment z, are shown in Figure 5c. This analysis leads to the definition of an interval, increment z, element of 0, 0.4, to filter out molecules during the molecular generation process. The generation of molecular structures involves sampling multiple values for n, from n, micro, sigma, for fixed m equals m, where micro and sigma are calculated using equations 6 and 7, respectively. Each sample corresponds to a set of targeted and non-targeted properties MLNs, which is fed to the model to generate a Coulomb matrix sample CMS. The VAE encoder is used to encode the samples, and the resulting latent representation encoding ZS is used to filter the samples based on the criteria increment Z equals ZZS, element of 0, 0.4. The generated molecules are then screened by analyzing the bond structure and the maximum force component, which must be lower than a threshold of 10 A.U. The structures undergo geometry optimizations using DFTB3 plus MBD, and their QM properties are calculated at the PBE0 plus MBD level of theory to enable comparison with the target values, M, in the QM7X dataset. The procedure is applied to navigate through the alpha EMBD space and alpha zeta space, which are two relevant property spaces for molecular reconstruction. The moderate degree of correlation between these properties of QM7X molecules allows for the intrinsic freedom of design in CCS when searching for molecules with desired functionality. 15 samples per targeted pair of QM properties are generated in both 2D property spaces, with targeted alpha values selected to generate medium to large-sized molecules and targeted EMBD and zeta values chosen to tune the topological effects. This study showcases the model's ability to generate diverse molecular structures, similar to those found in QM7X molecules, using only quantum mechanical properties as input. The results are presented in two-dimensional property spaces, one defined by molecular polarizability and MBD energy, alpha EMBD space, and another by molecular polarizability and total dipole moment, alpha zeta space. In the alpha EMBD space, the model performs better for molecular reconstruction when targeting extensive properties, which can be attributed to the purely geometrical chemical definition of the CM representation. The epsilon value, measuring the deviation between calculated and target values of a property, is approximately 9.2% for EMBD and 3.5% for alpha for the 15-molecule set. Focusing on the top 5 molecule set, these values decrease to 3.2% for EMBD and 1.3% for alpha. In the alpha zeta space, the epsilon value for alpha is 2.8%, while the epsilon value for zeta is 5.9% for the top 5 molecule set. The spread of generated molecules, or the flexibility of the model in molecular generation, can be explained by analyzing the relative variance of the conditional multi-Gaussian distributions of the non-targeted QM properties. Molecules generated with the highest precision have lower negative log likelihood values and small relative variances in extensive non-targeted properties, suggesting that controlling the degree of flexibility when designing molecules in targeted regions of a given property space may be achieved by adjusting the variance in extensive properties. This is evident in the generated molecules, where those in the EMBD alpha space display a greater diversity in heavy atom composition compared to those in the alpha zeta space. The modified molecular generation procedure, which retrained the model to treat molecular fragments more independently, demonstrates its impact on multiple targets across the alpha EMBD space. This approach enables the creation of novel molecular structures, showcasing the potential of a CCS parameterization that utilizes QM properties as intrinsic coordinates. The results indicate that the model can effectively navigate the space of molecular structures spanned by the QM7X dataset, producing molecules with diverse compositions and structures. However, the model exhibits limitations in navigating scaffolds not present in the dataset, revealing a deficiency in handling novel chemistry. In the realm of computational chemistry, a novel approach has emerged to generate interpolated geometries for different pairs of conformational isomers using geodesic interpolation algorithm in variational autoencoders, VAEs. This innovative method leverages the latent representation as an intrinsic coordinate system, which is pivotal for understanding molecular transformations. To validate this approach, researchers compared the generated geometries with new transition structures obtained through machine learning nudged elastic band calculations. The results showcased the efficacy of latent representation as a powerful tool in understanding molecular transformations, providing insights into the conformational changes that molecules undergo. However, despite these promising findings, there are limitations to this method. Generative models struggle to extrapolate to larger molecules, highlighting the need for further studies to investigate more advanced representations and datasets. This underscores the importance of continued research in this field to refine and expand upon these techniques. The use of geodesic interpolation algorithm in VAEs offers a new perspective on understanding molecular transformations, providing a more nuanced understanding of how molecules change their conformations. As researchers delve deeper into this area, they must address the challenges posed by larger molecules and strive to develop more sophisticated models capable of capturing complex transformations accurately. The property-to-structure relationship defined by the model is applied to generate initial configurations for molecular structures. This process utilizes a gradient descent algorithm that minimizes a loss function, ensuring continuity in the property space. The results demonstrate the model's capability in producing plausible geometries for transition paths of isomerizations. However, it also highlights the sensitivity of the CM representation to small changes, leading to artifacts in some cases. The generated transition geometries are then used as initial guesses for nudged elastic band calculations, which show a good agreement with the true minimum energy path. In the realm of drug discovery, accurately capturing molecular representation is crucial for effective screening pipelines. This requires refining molecular representations to encompass both geometric and electronic features. Expanding quantum mechanics datasets to cover a broader range of chemical and conformational diversity is essential, spanning from small to extended molecules. This study aims to motivate future research endeavors focused on advancing generative models by leveraging physical and chemical design rules obtained from structure property-property relationships. By doing so, enhanced models can be developed, offering increased accuracy for geometry reconstruction while preserving the high interpretability of the presented approach. The integration of physical and chemical design rules is critical for developing more accurate and interpretable generative models. This approach enables the incorporation of domain knowledge into machine learning models, facilitating the generation of molecules that satisfy specific properties and constraints. By leveraging structure property-property relationships, researchers can identify key molecular features that govern specific properties, leading to more targeted and efficient drug discovery pipelines. The authors acknowledge the financial support provided by the European Union's Horizon 2020 Research and Innovation Programme under the Marie Sklodowska-Curie Grant Agreement No. 956832, Advanced Machine Learning for Innovative Drug Discovery, AIDD. Additionally, they acknowledge the computational resources provided by the High Performance Computing, HPC, of the University of Luxembourg. The implementation, training, and testing code, along with a reproducibility notebook, will be made available on GitHub, ensuring transparency and facilitating future research endeavors. The research papers on inverse design in materials science and drug discovery employ deep learning models for intelligent discovery of organic molecules, drug design from protein target sequences, and machine learning-based inverse design methods. They also explore the application of chemical language models for de novo drug design, and machine learning accelerates the investigation of targeted MOFs. I'm happy to help. However, it seems like there is no content provided for me to refine. Please provide the transcript from the research paper, and I'll be happy to assist you in refining it into a concise and technically accurate summary suitable for voiceover narration. The authors cite various studies demonstrating that deep learning models, particularly convolutional neural networks, CNNs, have achieved state-of-the-art performance in image classification tasks. However, these models are often criticized for their lack of interpretability, making it challenging to understand the reasoning behind their predictions. To address this limitation, the authors propose a novel approach called deep lift, which is a technique for explaining the predictions of CNNs. Deep lift is based on the concept of feature importance, which is a measure of how much each feature contributes to the model's prediction. By analyzing the gradients of the output with respect to the input features, deep lift can identify the most relevant features driving the model's predictions. The authors also introduce a novel metric called the importance score, which quantifies the contribution of each feature to the model's prediction. This score is computed by backpropagating the gradients of the output with respect to the input features, and then normalizing the resulting values. The authors demonstrate the effectiveness of deep lift on several image classification benchmarks, including the CIFAR10 and ImageNet datasets. The results show that deep lift can identify the most relevant features driving the model's predictions, providing insights into the decision-making process of CNNs. Furthermore, the authors discuss the limitations of their approach, including the assumption that the model's predictions are linear with respect to the input features. They also highlight the need for future work to extend deep lift to more complex models and tasks.